Okay, in these slides we want to see a feature of the concept of potential that's very important. So let's start with this definition that we gave before, the relationship between electric field and potential. This is each component on its own. We defined this before. Let's say this is a region of space and the charge distribution is not shown, but these are values of the potential at certain points in space. Of course, the potential is defined at every point in space, but we're just showing you here some of the points, not all the points. So the potential here is 23.5 volts. The potential here is 123.4, and so on. These are just arbitrary numbers just to explain the idea that I want to show. So what if we go to every point in space and we add the same number at every point in space? For instance, what if someone decides, no, I want the potential here, instead of being 23.5, I want to add 5 at that point, and add 5 here, and add 5 here, and add 5 here, and add 5 here. Everywhere, every point in space, I want to add 5 volts. If someone else says, no, I don't want to add 5, I want to add 24.3 at every single point in space. So the idea is, if you add a constant, the same number, at every single point in space to the potential, will the electric field you obtain from this new potential field, will it be the same as the electric field from the old one or not? And to see that, we go back to the definition of electric field, Ex. If you add a constant to the potential, when you get partial by partial x of this new potential, the derivative of a constant is 0. So you get exactly the same Ex as you would that if the constant wasn't there. So the idea is that by adding a constant to the potential at every single point in space, when you get Ex or Ey or Ez, they turn out exactly the same as they were without having the constant there in the first place. So adding a constant at every single point in space doesn't affect the electric field that's obtained. And the electric field is the important thing, because Q times the electric field is the force, and the force is the physical thing that has to be the same in any kind of theoretical description you're doing. So since adding a constant at every single point in space doesn't change the electric field, then that means it's the same problem exactly. It's giving you the same physical solution. So to summarize this, you could have different people telling you that the potential at certain point in space is a different number. Someone could say the potential here is 23.5. Another person could say the potential here is 23.5 plus 24.3. The value of the potential at a point in space itself is not indicative of anything. But if you get the difference in potential between 2 points, the difference in potential between 2 points always has a fixed value. For instance, if I get the difference in potential between this point and this point, the difference is 123.4 minus 23.5. Having this extra constant added here and here, it won't affect the difference. So if this number was 5 and here it was 5, when you get the difference in potential, they will cancel out. No matter what constant number you add here and here, when you get the difference in potential between 2 points, the difference in potential always is a single value. So this is an important feature of the concept of potential. Adding a constant at every single point in space doesn't affect the physics of the problem. You get exactly the same electric field.
For example, another way to illustrate this is if we take the old problem that we solved in a previous video, where you had the potential given as a function of x and y. Now, what if we add the constant 45.6 volts to the potential? If you solve the problem again to get the magnitude of the electric field, or the electric field in general at any point, will the electric field, when you obtain the electric field, will you get a different result? Try it and see. Of course, you won't get a different result. You get exactly the same result, because when you get the electric field, you're getting the derivative of potential with respect to position. And when you add a constant, when you take the derivative of the constant with respect to x or with respect to y, it gives you 0. So it doesn't affect the result at all. Another example we can show, what if they give you in a problem how the potential changes as a function of x, and it's given by this straight line, and so you can calculate the slope of the straight line using the given information to get the electric field in the x direction, and you can also get the slope for the y. They give you the potential as a function of y, which is this straight line, and you can get this, use the slope to get EY. And the question is, what if you add a constant to the potential everywhere, like here, you shift the curve upwards by 50 volts. Here, shift the curve upwards by 50 volts. So the slope is exactly the same. Since the slope is exactly the same, when you calculate partial v by partial x, which is the slope, or partial v by partial y, which is the slope, you always get the same number. So the electric field you obtain, Ex or Ey, will be exactly the same. So that's what we mean by adding a constant to the potential everywhere in space. It doesn't affect the value of the electric field.